Welcome, and today I'm going to be looking at the VL53L0X laser ranging sensor. Now this is a sensor that can sense distance using an infrared beam. Now I did do a video on this sensor many years ago, but it was just a brief overview, and I really always wanted to go back and make a better video, so hopefully today's will be better than the first attempt. So here we are with the webcam. I've got two versions of this board. Now I'm going to be honest straight up, the version here, the black version, I have found to be a better version than this board. I thought the chips would be identical on both boards, but actually looking at them, this chip seems to be slightly smaller than this chip, and I think is even mounted slightly differently. What I have found is that this version here seems to have a better range than this version, and in general seems to be more stable. You'll notice I put the pen by the side just to give you an idea of size. Both of these items are very small. Now the way they work is they send out an infrared beam that will then bounce off something, come back, and it will be able to work out how long it took that beam to return. One thing about infrared to be aware of, obviously you can't see it, but it doesn't mean that it can't damage your eyes. So again, just make sure that you're not pointing this into your eyes, and that's especially worth thinking about with your project. I tend to use these things for model railways, and it's just important then that, if you like, the beam isn't firing off the edge of a layout at the height that children are going to be looking at the layout. So just bear in mind, you know, safety first with all of these things. So that is, if you like, the size of the chips, of the little units. Let's just take a look at how to wire them up. So as always, there is a link below the video to the Digital Town website, to the components page, and if you follow that link you will come to this page that I will show you now. So you'll finish up on the Digital Town website on the components page, just go down to the VL53L0X and click on that, and it will bring you down to the resource area. Now I've taken the photographs of the unit. Again, not the greatest because they're such a small unit to photograph, but just so you can try and get a better look. I have also put an image of the library and some details of the library that we're going to use. I'm going to go through some of the issues with the various libraries in a bit, and then obviously we have the circuit diagram. Click on the circuit diagram for a larger version. Now you'll notice I have two circuit diagrams. We have the one circuit diagram here if you're just using a single board. Now these are I2C, so you're going to use the wire library, and on the Arduino Uno, if we go to our wire documentation, we have the SDA and the SCL pins, and they are on pins A4 and A5. So that is why A4 and A5 are in use here. And if you're using a single sensor, you just need to connect the pins up to the SDA and the SCL on the sensor. Obviously connect your 5 volts. They are 5 volt tolerant, these units, but if you're using an ESP32 or some other Arduinos, they'll run on 3.3 volts. That is the simple setup if you are just going to use one of these units. If you want to use two of these units, then things become a little bit more complicated, and you need to have a connection between the X shut pin and a pin on the Uno, and that is because of the way that the addresses work on these units. So coming back to the webcam, these are some PCA 9685 boards. These also run on I2C using the wire library. And when you want to change the address on these, you solder across some of these little tabs here. As you can see, I've got one soldered across on here. That means that when you change the address by soldering the tab, the address is changed permanently on the board. With these sensors, it's very, very different. The address needs to be set in software each time the board is started up, which means that you have to put the X shut pin low while you set the address on one board, then put this X shut pin low while you set the address on the other board. Otherwise, obviously, you'll send the same address to both, and that is not good. You need different addresses. But it's just something to be aware of. The addresses that are valid for these, I think, is 0 to 127. And I think it's address 29 that you can't use, but you just need to check that out. I've been using addresses sort of 30 to 127, and all my tests on those addresses have been fine. But it's worth noting that the address has to be set up in your setup code, and I'll address that in one of the later sketches. Now, one of the other issues to consider is the way that these units work. When I first bought these, I was thinking of replacing these ultrasonic sensors on my robot car. The idea was that this would be more accurate in sensing the distance. However, there is a problem. If we put this on its side, when this unit works, it sends out a cone of sound, if you like, that reflects, and it will pick up anything within a 30-degree angle. Now, the problem is when you put these on their side and fire the beam out, let's just get some blue tack. What happens now is the beam comes out in basically a straight line and reflects back. Now that means that anything in this area here that this unit would pick up, this unit will not pick up. So although these units have their advantages in some ways, I don't regard them as being as useful for things like a robot car, because on my robot car I can put 3 of these in a row on the front of the car, and I can cover a 90-degree angle by slightly tilting these. If I put 3 of these units on the front, what I would finish up with is 3 very accurate lines, but anything such as a table leg could sort of sneak between the gap here and the vehicle would crash. So these units have their uses, but unfortunately, if you're thinking of using them on your sort of obstacle avoidance robot car, they're probably not the best item. So coming back to the wiring diagram, what I'm going to do is start off by doing a single sensor. So going back now again to the webcam, what I've done to try and demonstrate this, obviously I've got the Arduino slightly off camera on the right. Here is the actual sensor. I've tried to line it up with the 0 on my rule. The sensor I'm using this time is one of these black sensors, and what I have down here is a box that I can move backwards and forwards to check the distance. So when it comes to coding up these units, you're going to need a library. So just type in VL53L0X, do a quick search, and as you can see, there are a number of libraries that appear. Now, I have been testing these libraries over the last few days. As you can see, I've got a lot of these libraries installed, and I'm going to start with the Adafruit library because that's the library that I used last time I used one of these sensors. And of course, one of the problems is libraries change. So what we're going to do is go to the file examples, Adafruit, where are we? We're going to go down to the VL53L0X, and I'm going to go for continuous. Now, continuous means that it is constantly checking the distance, rather than if you have a single where it just fires off a single beam. So let's just take this example and have a look at what happens when we compile it up. So let's just get this thing compiled. Now, the first thing that shocked me when I compiled this was this warning. And I must admit, I was a little bit nervous about this warning because it's talking about a left shift issue. And this is something that can happen in C++, where you can actually finish up reading things that are, if you like, out of range of the variable that you're using. It's a bit odd. You can finish up reading something that you shouldn't be reading. So that was a little bit worrying to me when I first saw it. But the other thing that I want you to notice is what happened down here. So the library for this single component, just to install this code, I have used 54% of the storage space of the Arduino and 58% of the dynamic memory. So realistically, I've used over half of the storage memory of the Arduino, and all we're going to do at the moment is read this thing. Now, despite the warning, if I bring up the serial monitor and let's get this thing running. So it's now running away. And as you can see, we've got the distance that it is saying that the unit is reading. However, if we now go to the webcam, what I'm now going to do is move my box along. So I'm going to move it to 140. That should be about right. And you'll see that the actual results I'm getting, if I just stop the serial monitor, I'm getting sort of 149, 150, 154. I must admit, the variance in this is a little bit concerning because I'm getting a 5mm sort of variance on this. There's 155 there, so that's actually a 6mm variance. And obviously, as you can see, nothing is moving and it should be reading 140. Now, I did find with most of the libraries there is some kind of error, and in my final solution I have actually removed the error from it. But it's just worth noting that error within the, if you like, the readings. Now, what I've now done is I have swapped over the unit and I've put that purplish coloured unit instead. Now, I haven't moved anything, and I'm just going to stop the serial monitor again. And I just want you to note the error range with this second chip. And this was something that really surprised me, that if you like, I'm getting nearly what, that's 25mm difference. And I was surprised between the two units. I was surprised at just how much they varied in their abilities. Now, I can't show you on the desktop because unfortunately my desktop is too small, but this, the purple unit, in fact I'll just pull it out so you can see it. So that is the purplish unit. This is the black unit that I had in before. The differences in these were quite amazing. I found that this purplish unit really wasn't much good past 250mm, whereas this unit I was finding was being quite accurate up to a meter. Now, I don't know what they claim is the actual range of these things, but beyond 1 meter this started to fail. Beyond sort of 250mm, certainly by 300mm, this was a complete waste of time. And so that's why I would recommend looking for this type of chip rather than this one. Now, to make it easier to find the chip, I put a link to where I bought these on Amazon. Let's just bring that link up. And when you go to the link, mine has got this VL53L0X V2. Of these, this was this one rather than the slightly cheaper one. I'm not saying that you buy them through this link. You know, I'll be honest, I get a commission if you do, but don't worry. What I was mainly interested in was having a sort of a decent picture of the link so that you can search for these either on Amazon or wherever you buy your components from. But this one was definitely the better board, and it's going to be the board that I'm going to use for the rest of this tutorial. So I'm now back to the black chip again. Just looking at the output, you can see that it is a far more stable result that I'm getting. Also, as I move the box backwards, I'm now sort of back at 300 millimeters, and you can see that I'm still getting sort of a 20 millimeter error, but I can get rid of that later with a little bit of software. And if there wasn't a barrier in the way, and if I move the thing out of the way altogether, you can see it's going to nearly 500 millimeters. It's not going to get any further than that because there's a wall in the way. But testing it around the room, I was able to get about 1 meter, I think it was 1100 millimeters, that I could just about stretch it to, but I would sort of say that the limit realistically is about 1 meter. Anyway, going back to the Adafruit example, I'm not quite sure what is going on with this error. It didn't seem to happen in every one of the examples, but as I wanted continuous, this was a problem. Now, I'm not sure the problem is necessarily Adafruit itself. I think it has got something to do with this API core, because some of the other libraries that use the same core have exactly the same error. So going back to the libraries, I then went through the big sort of search looking for, if you like, what I would find as the best library. And you can see I tried the Pololu one, I tried the DF Robot one. Now the DF Robot one, just looking at my details, that used 19% and 24% of the global variables. I went through various ones. I used the Grove ranging sensor library, but the library that I finally settled on is this one, the VL53L0X_mod by Schnoog. Hope I've pronounced your name right. There is more info available if you just click on this link, and there's actually some quite useful information on actually how to use the library. A lot of these libraries, I must admit, I didn't find the examples or the documentation particularly easy to use. So this particular library is the one I'm going to use, and one of the reasons I'm going to use it is it takes up such a small amount of space. Now again, going back to the resource page, I have put an image of the library name so you can look for it in your Arduino IDE, or there is a link here to download it from GitHub. And again, if you go to the GitHub page, it's going to give you, if you like, the README, the instructions on how to use the library. So we're going to now use this library, going down again into the examples, and it is VL53L0X_mod, and you want the continuous non-blocking. I prefer non-blocking code for obvious reasons. You will get better results, so go for the non-blocking version, which was another bonus with this library. So let's just bring that up. So as you can see, it's a fairly simple system. Include the wire library, include obviously the library that we've got. We then set up an instance of the library. We're going to call it sensor. And then in the setup, we've just got the serial beginning, start the wire library. There is a timeout for the sensor. I would leave that as 500. And then basically we initiate the sensor, we start it up. If it doesn't start up, you'll get a failure. Most of the failures I have had is because of poor wiring. In fact, it's always been poor wiring. And then we're going to start the sensor running in continuous mode at a 200 millisecond interval. That's the setup. Coming down to the loop, we have a variable that we're going to call new measurement, and all it's going to do is when a new measurement is available in the non-blocking, it's going to basically print out the distance. So let's get that running. Now, before we look at the actual output, I just want you to notice that this is only using 24% of program storage space and 22% of my sort of local variable space. So by using this library, I'm using half the space of that Adafruit library. And this is just one of these things that you need to be aware of, that not all libraries are equal. It could be that the Adafruit has more stuff in it, more functions in there, but it's always that danger that if you like, you put more and more stuff into something and it uses up more space. So this library is using less space, which would allow you more space for any other code. Right, let's look at the output. As we can see, it is rushing away. I'm just going to move my barrier to 150 millimeters and stop the output. And as you can see, I'm getting a variance here, 165 to 170. So I'm seeing about a 5 millimeter variance, which for my sort of projects is okay. I've already come to the conclusion with these units that they're not going to be sort of millimeter accurate. In the one of the libraries, in fact it might be the Adafruit, you can set it supposedly that you're getting down to 0.25 of a millimeter. Well, with the variation that I'm seeing, that's going to be an absolute load of rubbish. So yeah, it's reasonably accurate. You know, it would be usable for certain projects, but if you're going to use it to measure the size of your room to make something, it's not the component you want to be using. So that shows basically the simple setup to get the unit working. Now, the first thing I want to address is the fact that this is incorrect. If we bring the video back in, we are at 150 and this is saying 166. So I'm going to show you how to, if you like, make this value more accurate. We're going to calibrate the system. So what I've now done, I've made a copy of that previous sketch and I've renamed it so that I know what it's to do with. Just so you can understand my naming system, it was the VL53 continuous version, and I put an underscore because I'm using the VL53L0X mod library and it's version 1 of this code. The reason for naming it with such a long name was so that I would actually remember which library and which sketch it was based on. Right, coming down to the main loop, the only change I've made is I've cut out a lot of the excess code, and as you can see, the serial monitor now is just reading a set of numbers going by. Now, the first thing I'm going to do is move my barrier to 50 millimeters. So now if I stop the serial monitor, I can see that I'm getting a value there that looks to me like the average value is going to be about 64. So at 50 millimeters, it's reading 64 millimeters. I'm now going to restart the serial monitor. I'm going to move this back to 250 millimeters. Let's stop that again, and we can see we're getting values there. They seem to be mainly, there's one odd one there, but on the whole it's sort of 272 to 275. So I'm going to go with 273. So let's type in 273 millimeters. So we now have the real distance, and then we have what we're actually getting out. And what we're now going to do is put a little bit of code in so that we get the correct distance coming out of our code. So the mod that I've made is very, very simple. I've added a new variable and I've called it cal measurement. It stands for the calibrated measurement. And all we're going to do now is we're going to serial print out the new measurement, and then we're going to use the map function. So what we're saying now is we're going to put the value in for the new measurement, and what I'm saying now is if the value is 64, that would map to 50, and if the value was 273, that would map to 250. Then we're going to print a C and the calibrated measurement. So let's bring that up and bring the video recorder back in. So at the moment the box is still sitting at 250 millimeters on my rule, and if we look at the values, that looks to me on average to be about right. So we'll just keep that scrolling, and then I'm going to move my barrier up to the 50 millimeter mark, and let's see what we get there. So at 50 millimeters we're getting values between, we are getting a 50 now and again up to 54. That looks like it needs to be changed, just increase slightly. I'm going to increase that to 66. Let's just compile it again. Stop that again, and now you see I'm getting a value that's pretty much around the 50 mark. Sorry about the camera, it sort of blocks the rule. We're now going to move it back to, let's put it to 140, so you can see what's going on, and you can see we're still getting a little bit of error, but it's pretty much close enough. You can just play around with these values until you get it absolutely right, or if you like, as accurate as you need it for your project. So if you're just wanting to use a single reader, this piece of code will work. And if we go back to the Digital Town website, if you click on this link, you can download all the sketches plus circuit diagrams. All the sketches for today's lesson will be there for download. So coming back to the code, if you need to tweak the calibration, it is just these two variables here that you need to alter. Right, I think that is about it for controlling one of these sensors. We're now going to look at how to control two or more sensors. Now the first thing, if we're going to use two sensors, you cannot have I2C devices with the same address, and because there's no solder pads on these units, we're going to have to learn to change the address in software. So let's get started with changing addresses. So I'm going to start just with a single unit. So let's imagine that you now have another item on the I2C bus that is using the default address that the VL53L0X has. So we're just going to change the one address. I've created a new copy of the last sketch. The big change that I've made is in the main loop. I've commented everything out because that's not of any use to us right now. And what we're going to do is I have brought up the documentation for the library, and the two functions that we're going to use on this occasion are set address and get address. Now the set address value is a 7-bit address. So if I bring up my calculator, it says looking for it, there we go. Let's put it into programming mode. A 7-bit address, if we put ourselves in binary mode, 1, 2, 3, 4, 5, 6, 7. So a 7-bit address has a decimal max value of 127 as the maximum value. So realistically, if you want to use addresses between, I use values between 30 and 127, they will work fine. Now what I've done for this example, I'm going to set the address to 100, and then I am going to use the function get address. So I'm going to set the address, set the timeout, initiate the sensor, start the sensor, and then I'm going to get it to print out the address. So let's get that uploaded and get started. Start the serial monitor, and there we go. You can see I've tested it once already, and I am now getting the correct address. Now what I'm going to do is uncomment all of this, upload it again, and this time not only should I get the value 100, which we will only see for a fraction of a second, there we go, we're now getting correct values. And if I scroll back up to the top, we are now using address 100, and we are getting the values just as we did before. So that is how to set the address with a single unit. Now a single unit is easy. The problem with using multiple sensors is that if I send out a transmission to set the address, it's going to set the address of any unit. It's just not going to work. So this is where there is a pin here called the X shut, and this is a way of turning, if you like, the sensor on and off. So the way you would program this is you would turn off one sensor, set the address for the other sensor, then you can turn that one off and set the address for the first sensor. Or alternatively, if you're going to use the default address, all you need to do is turn the one unit off, set the address for the second unit, turn the first unit back on, and you're away. And so that's what we're going to do in this example. We're going to turn one unit off, set the address for the second unit, and then turn both the units on and get them running. Now if you do want to add 3 or 4 sensors, then what you will need to do is obviously turn 3 sensors off. If there were 4 sensors, you need to turn 3 sensors off, set one address, turn that one off, turn the next one on, set its address, turn that one off, turn the next one on, and set that address. So you just need to make sure that the ones that you are not setting the address are shut off while you set the address. Right, let's get on with some coding. So here we are with the code. Let's just move that down. So this is version 3 of the code. Now the big changes that I've made from the circuit is obviously we had sensor before. I've now added sensor 1, so we have two, if you like, versions of the library running at once. The sensor pins, I've got the first sensor is attached to pin 10, that is for the X shut, and sensor 1 is on pin 9. So again, looking at the circuit, that is this brown wire and the blue wire. Coming down to the setup, the first thing that we need to do is set those two pins as outputs, and immediately I'm going to set the sensor low, and I'm going to, it's this sensor that is going low. We're setting this pin low. At that point, we have now shut down that sensor. I'm then going to make sure that sensor 1, the X shut pin, is set high. That means it's now ready to receive some information. We're going to put a delay in of 10 milliseconds just to let it settle down. And this time I'm going to set the address as 127. Then what we're going to do is start sensor 1. We're going to initiate it. Obviously, if it fails, it's going to let us know. We're going to set it in continuous mode, speed of 200, and I'm going to tell it to print out the address. So I should see 127 printed out. Then what I'm going to do is turn on sensor 1. And again, just put that delay, 10 milliseconds, just to let it settle. Go through the initiation, and I'm also going to serial print out the address. Now at the moment I've commented out the main loop so that we just see these values. So let's have a look at what happens on the serial monitor. There we go. So we've got 127 is the address that I set, and 41 is the default address for these units. Just in case you don't realize that, 41 is their default address. Right, that is that bit. Now I'm going to uncomment the main loop. And again, just as before, we have new measurement, and I've got a variable measurement for the final variable. This time I'm going to serial print out just this thing sen 0, just so that I know it's sensor 0. I'm going to print out the measurement just as we did before. Then I'm going to remap it, and once again I'm going to then print out the measurement. Then I'm going to do exactly the same for sensor 1. So sensor 1, we're going to get the value in new measurement. We're going to print out the new measurement, remap it, and then once again serial print it out to get the final value. So let's just get that uploaded. There we are, serial monitor is running. Now if I just bring in the camera, you'll see at the moment, if I stop this, that I'm getting two pretty crazy values. Sensor 1 is reading 496. Now sensor 1 is this one. You can see sensor 0 has gone off the scale at 8,000. That's because it's pointing up at the ceiling. So let's get that running again. And what I'm going to do now is start to put my hand over it. And as you can see, both of the sensor values are changing, or I can just block one, or I can block the other one. So as you can see, that is all working correctly. Now going back up into the code, if you are going to do 3 sensors, 4 sensors, whatever, what I would tend to do then is you would set the pin high for sensor 1, set the address, then immediately under here you would set the pin low, and then set the pin high for sensor 2, set its address, set it low, set number 3 high, set its address, set it low, then set all of the X-shut pins high, and then you would do, if you like, this bit of code followed by this bit, and if you like, work through all 4 of the sensors. So that is the way I would tend to do it if I was using more sensors. So going back to the webcam, just an odd thing that I noticed having them at this angle, you can actually just see the laser, if you like, is pulsing on both of these. You can see it pulses every 200 milliseconds. As you can see though, it is all working, and I hope that's been really useful to you. It's an interesting component. As I said, I definitely prefer this unit over this unit. I found this to be more stable. It might be worthwhile if I could have checked some other units, but I can't just keep ordering endless sensors to test them. But I think that's about it for today. So a pretty useful sensor. I shall be testing these on a model railway because they will allow me to check if something is blocking the track in certain positions without having to have a pickup on the other side. Because they're so small, they'll be pretty useful to hide in buildings. Again, they could be useful in your sort of robot type creations for sensing the distance of certain things, although I'm not sure that they are suitable for your obstacle avoiding cars. But I think that's it for today. Please, if it's been useful, please click the like and subscribe because it really does help the channel. And any questions, please either email me off the Digital Town site or put your questions in the comments under the video. Thanks for watching, and I'll see you in the next video. Bye for now.